start apparently. So I will be writing on this famous board, okay? So there'll be no transparencies or anything like this. So I will be talking about sparse recovery problem in convex hull of a given dictionary. And this is basically in the paper that my paper that will appear in the Annals of Statistics sometimes, I don't know, this year or early next year, okay? It's already there, yeah, it's on the way, okay? So the problem is as follows. Imagine that, let me use this board probably. Imagine that we have a random couple xy that takes values. So this is a random couple. A random couple in S cross T, and T will be always a part of real line, and S is more or less arbitrary space. Okay? And I will just introduce some notations that I will use all the time. So I will assume that P is the distribution of this couple, and marginal distribution of X I will denote capital pi. Okay, this will be marginal distribution of X. And then I have data that consist of IID copies of this couple xy, IID copies of xy, and what I want, basically, I want to predict y based on an observation of x and based on the data, of course, right? Which means that I want to find a function that maps s into R such that y is, about the same as f of x. And in order to describe precisely what means about the same, I probably have to introduce loss and measure this by some risk, right? Yeah.
Are you leaving T as a general subset of R? You want to cover it?
Well, I will cover, it will cover a couple of situations. T can be an interval in R, for instance, and it can be a regression problem, or T can be -1 and +1. It can be binary classification. There are several things that can be included here, but it does not matter that much. And then, I will denote LYU. This will be my loss, and then if I write expectation of Ly f of x, so this measures the loss I suffer if I use f of x as a predictor of y, right? And expectation of this loss is my risk, and I will, use this short notation for the risk in this situation. So I have kind of superposition of loss and my action f, if you want, right? My function f, and then I'm integrating this with respect to the distribution of the couple, right? With respect to the distribution of the couple. Okay. And, I will denote, maybe I will need it once in a while, and I will assume for simplicity that this minimum exists. And this minimum is over all sensible functions, say, measurable functions, okay? And then I will denote E of f. It will be just the difference between the risk of f and the minimal possible risk in my problem. So this is what in machine learning literature often called excess risk. Okay, it will be excess risk. And now, what will be my assumptions on the loss? Okay, on the loss, I will just prefer to describe it vaguely that this will be loss of let me write quadratic type. okay, which of course means that that this loss is included. Okay, that this loss is included, but essentially what I want this function to be convex with respect to u, right? It will be convex with respect to u. As you will see in a minute, I will be always in the situation when the range of functions at which I am looking will be bounded. So in addition to this, I will assume that the loss is, say, twice continuously differentiable with respect to u, right? And then the first and the second derivative will be automatically bounded in any finite range, right? And then I will also assume that the second derivative is strictly positive, so essentially I have strict convexity in this problem. Okay, so this is basically what I will just call loss of quadratic type. Okay, so in this case, the excess risk, right? It's easy to see that under these assumptions, of course, the excess risk will be up to constants. Will be just the square of the L2 distance between f and this function, right, at which the risk is minimized, right? So essentially, we are not that far from regression here, right? Not that far from regression. Also, you know, there are many losses used in binary classification, for instance, right? That also are of this type. But I'm not going to use Hilbertian structure, okay, in any way. But you know, essentially, I'm trying to have my problem close enough to regression problem. Okay. Now, okay. So what? Since I want to talk about sparsity, you know, let me also introduce some further notations here. So I will be looking at a finite collection of functions from S. Let me make their range bounded into -1, 1, okay, and this will be my dictionary. And I am interested in the situation when capital N will be rather large, say larger than the number of than the sample size, right? In my problem, which is small n, right? Maybe much larger. Okay, and then you know I will denote f lambda. It will be just some of lambda j for lambda in Rn, for vector lambda in Rn, and I will be interested, in fact, only in finding a good approximation for f star in the convex hull of H. So I will be looking kind of at convex aggregation problem, right, in this context. So the convex hull, of course, consists of all linear combinations such that lambda is in the simplex of all discrete probability distributions, right? On a capital N point set, right? On a capital N point set, and then you know how I'm going to try to find a good function f to solve this prediction problem. Okay, to solve this prediction problem, I will be doing this by certain empirical risk minimization with adding certain penalty. Okay, certain penalty. So you know I already wrote what is risk, right? Risk can be estimated by empirical risk, right? Just the average loss on the training data, and for this one I will use this notation, just to write it shorter. So just integral of this superposition with respect to empirical distribution Pn, okay, of my training data. Okay, and then here will be actually the way I will be trying to solve this problem. I will be looking at the following problem. I will be minimizing empirical risk over the convex hull of the dictionary, and I will be adding to empirical risk complexity penalty, which will be like this. It will be some epsilon, which will be regularization parameter, and it will be multiplied by this thing, and then minimized over all lambda from the simplex of all probability distributions, right? And what we have here, of course, this is just entropy, right? Just entropy of the distribution lambda, right? With minus, right? With minus. So when I make it negative, I'm making this thing convex, right? So the loss already is convex. So as a result, I'm ending up with a convex minimization problem. I'm minimizing on the simplex, which is also a convex set. Okay, minimizing on the simplex, which is also a convex set. So this penalty here plays about the same role as L1 norm plays when we are minimizing over the whole linear span instead of minimizing over the convex hull. Also, it's a little bit counterintuitive, as the referee told me. This paper, so I did not think about this as counterintuitive, but indeed it is a little bit counterintuitive. Well, because we know well that the entropy is maximized on the uniform distribution, right? So minus h of lambda is minimized on the uniform distribution, so it means that in a way we are penalizing for sparsity rather than penalizing for non-sparsity. Okay, this is what intuition tells us. However, on the other hand, it's easy to see that this is not actually that far from the L1 norm that is usually used for. It's a convex function that we are using here that is pretty close to L1 norm. Okay, it's strictly convex. Of course, it's a little bit better even in some sense, but it's pretty close to the L1 norm. So we have to just to do some analysis in order to understand what is happening here, and analysis shows that you can probably forget about intuition and just live with the fact that you are getting some form of sparse recovery, okay, with this type of method. Okay, but actually, let me introduce here one notation. So I will denote lambda hat epsilon will be solution of this problem, right? This is the vector at which the minimum is attained, say. Okay, in this problem, it's actually, I guess it should be unique because this is strictly convex. Okay, this is strictly convex. Okay, so now. In addition to this minimization problem, just to compare it with something, let me write down another convex minimization problem. I will just, instead of Pn, write P here, the true risk. So I'm also minimizing this over the simplex, and let me call the solution of this problem lambda epsilon. Okay, lambda epsilon. Then basically my goal will be to try to answer a couple of questions here related to these two problems. So the first question, so these are the questions I will try to answer. The first question is the following. Imagine that for whatever reason this vector lambda epsilon happened to be approximately sparse. Okay, it's a little vague, but let me write it. Is approximately sparse. And but basically, by the way, precisely because of this point that I already mentioned, that the entropy in some sense penalizes for sparsity, right? It cannot be, it's easy to see that it cannot be precisely sparse, okay? It cannot have, you know, zeros in a number of places, actually, okay? But still, if it happens that, that there is a sparse vector lambda, right? A sparse vector lambda such that it makes this thing very small, right? It makes this thing very small, make it close to its minimum, right? Then apparently when we are adding penalty, what the penalty would do, it would redistribute the weights a little bit, okay? So it will, you know, the weights, there will be some weights in the places where there were zeros, right, if we are not using penalty, but there will be not that much weight there, okay? This is what will happen, okay? So to be a little bit more precise, by approximate sparsity, I would mean this, that there is a relatively small set of coordinates, right, such that outside this set, the L1 norm of what is outside is small. Okay, so I will be measuring the tail, the remainder, right, in L1 norm. This will be a more precise meaning of this. Okay, so imagine that lambda epsilon is approximately sparse. The question is whether this implies that lambda hat epsilon, the empirical solution, also is going to be approximately sparse with a high probability. With a high probability. Okay, this is one question. Another question actually related to this is the following. Again, if I know that lambda epsilon is approximately sparse, then does it imply that if I measure the distance between f lambda hat epsilon and f lambda epsilon between these two functions. For instance, it would be natural to measure this in L2, right? In L2 with respect to the distribution of the design variable, right? Because this is essentially what is related to to the natural excess risk in my problem, right? As it's written somewhere, right? Does it imply that this will be small? And by small, usually, you know, in a sparse recovery problem, we mean that we have nice control of a quantity like this. If it's of the order, say, d divided by n, where d is the degree of sparsity, right? Where d is the real dimension, right? That we are dealing with here. Okay. You know, if we can, in addition, say something about closeness of the vectors of coefficients themselves, right? Lambda hat epsilon and lambda epsilon, it would be also helpful. Okay, so that's kind of the second question. Now, the third question is related to the fact that we actually don't care that much about lambda epsilon, right? This is not what we really are interested in, because we just added some complexity penalty here, did some regularization that maybe is needed in this problem. It's not necessarily needed in this problem. So this is not what we care about, okay? So we want to relate the sparsity and, you know, kind of excess risk that corresponds to lambda epsilon to something that we care about, right? And the question can be formulated this way. Imagine that there exists a vector lambda in our simplex such that lambda is sparse, and at the same time the excess risk for this function f lambda is small. Okay? Since the excess risk is almost the L2 distance, you know, there exists a sparse vector that provides a good approximation in L2 sense of the target function f star. This is basically equivalent to this, right? And excess risk is small. And the question is, does it imply that lambda epsilon is, it can't be sparse, but it can be approximately sparse. And E of f lambda epsilon is small. Okay, so these are three questions I would like to try to answer, and the answer to the first two questions will be more or less definite yes. Okay, so by definite yes I mean that there will be no need to impose any assumptions on the dictionary except what I already imposed. Okay, nothing will be needed. It will be just true. Okay, and I will write certain inequalities that will show that this is correct with no extra assumptions. And the answer to the third question is very conditionally yes. Okay, so subject to certain constraints on the dictionary that are very common in sparse recovery problem, for instance, with L1 penalty, right? So we will need certain assumptions that essentially keep the dictionary not too far from being orthonormal in a way. Okay, so something of UUP flavor or this type of things. Yeah.
So if you know that 1 and 2 are true, then doesn't the hypothesis of 3 would tell you that lambda hat epsilon is approximately sparse, and then the excess risk of
Yeah.
f lambda hat epsilon is also small?
Yes, it will tell me this absolutely. If I know that this 3 is true, then it's very easy. This is precisely the point and why I am interested in this question. This 3 would immediately imply that the excess risk of f lambda hat epsilon also is small, so it would lead to what is called an oracle inequality. Okay, just can be derived in such a simple way that it's a corollary in my paper. Okay, from these 3 things. Okay, it's immediate. Yes.
When you talk about an L1 penalty, is that an L1 distance between lambda and the uniform distribution?
No. What do you mean L1 penalty? In the, when I'm talking,
Lambdas add up to 1, so the L1 penalty function equals 1.
But I'm not using this is precisely the reason why I am not using L1 penalty. I'm using entropy.
No, but you're saying that it's approximately close to the L1 penalty.
Well, I'm saying that the conditions that are needed for this third implication to be true, right? The conditions that are needed for this are of about the same flavor and what is needed in the case of L1 penalization over the linear span. Okay, L1 norm is used as a penalizer when we are searching for the solution in the whole linear span. I am looking only for the solution in the convex hull, so I'm using different penalty, but the conditions on the dictionary will be pretty close to what is needed in the case of L1 penalization. The only thing I'm saying. Okay.
What's the size of epsilon? Because, of course.
Oh, I will start formulating the theorem. There will be conditions, of course.
Right. Well, no, because I mean, in some sense, I mean, if epsilon is sort of not too small, then clearly, if I make capital N as large as possible, that penalty will dominate the.
Well, I will, if I have time, I will show you, the epsilon will be, you can use something like this, okay? This kind of standard, yeah. Okay, so let me start formulating the results, okay? So how much time do I have? Still have some, okay. Let me start formulating the results. So here is, the first theorem that provides, some answer to the questions number 1 and number 2, okay, and it will be under slightly worse assumption on the epsilon that is written here, okay, but I will later show you how to transform it into this assumption, okay, how to make it like this. Okay, so here is the theorem. So there will be no conditions actually, not really conditions, okay? So for any d, which can be anything, right? For any number d, and for any epsilon that is larger than, you know, there will be also d capital. Don't get confused with d small. D capital will be a constant that depends only on the loss function. So it's just a number, essentially. Okay. A will be anything bigger than 1. Okay. A will be anything bigger than 1. So for any epsilon like this, and for any subset J of the set of the coordinates of cardinality D, okay, I claim that the following is true, that with probability greater or equal than 1 minus capital N to the power minus A, capital N is the size of the dictionary, so it's with probability 1 for practical purposes, okay? So with probability 1, essentially, the following inequalities are true. So first two inequalities will tell us something about sparsity properties of the empirical solution and, you know, the relationship between empirical solution and the true solution from the point of view of sparsity. Okay, so it will be constant C like D depends only on the loss function, on nothing else, on the choice of the loss. Okay, so this is one inequality. Another inequality is similar, but it controls true solution in terms of empirical, just another way around. That's kind of two-sided in a way. With the same error term. And then maybe more importantly, this is what controls the square of the L2 distance between f lambda hat epsilon and f lambda epsilon. And in addition to this, I will add certain distance between the vectors of coefficients themselves. It will be also controlled automatically, so there will be epsilon here times k lambda epsilon, lambda hat epsilon, lambda epsilon, and from the very notation and from the fact that these are distributions, probability distributions, you can guess that this will be Kullback-Leibler distance. In fact, it's symmetrized Kullback-Leibler distance, so Kullback-Leibler divergence between this guy and this guy plus Kullback-Leibler divergence, you know, when we switch them. Okay, so it's symmetrized Kullback-Leibler distance. And this whole thing will be controlled by C, and then I will have this. It does not matter. Sometimes I write plus, sometimes I write maximum. It does not matter because I do not specify the constant.
What's script D, by the way?
What?
Script D.
This D?
Yes.
It's a constant that depends only on the loss function, only on the choice of the loss. And then I have to take maximum of this with the following thing. Okay, so this is what is happening. So, you know, essentially what you have to do, since this inequality applies to any set J, and you know, you can pick any D and any set J of cardinality D. right? Whichever you want. What would be a good strategy in order to get something meaningful from here? Okay, you would probably want to make this guy, right? To make this guy approximately of the same order as this square root, right? Then the whole error will be of the order d divided by n roughly, if you forget about logarithmic term, right? It will be d divided by n, right? So you just have to increase set j, pick it in an optimal way such that this, just leave in j only the largest coefficients, of course, right? And pick a set j in an optimal way, right, such that the tail, right, the L1 norm of the tail, this is what is written here, right, becomes smaller than square root of d plus log, right, divided by n, right, becomes smaller than this square root, right? You will have to make d large enough in order to achieve this goal, right? How large it is depends on the approximate sparsity. This is precisely what measures approximate sparsity of lambda epsilon, right? If it's really approximately sparse, it means that there are few large coefficients and the rest are small in the sense of L1 norm, then d will be small, right? Then d will be small. And then as a result, this d, which is kind of dimensionality in this problem, right, controls the size of these two quantities, right? And one quantity is the kind of the distance in the sense of prediction loss in this problem, right? Because we are measuring distance in L2 with respect to design distribution, right? With respect to design distribution, we are averaging with respect to design distribution in this L2, and another distance is the distance in the space of coefficients, and this is Kullback-Leibler distance, which kind of comes naturally from computation because we are using entropy penalization. Okay, so it's kind of natural that it occurs here. Okay, so this is one possible answer to the first two questions. And as you see,
your idea of sparsity here, it seems like you simply want them to be small. They don't actually have to be zero.
No, yes. It's approximate sparsity,
yeah.
And with this penalization, you cannot get sparsity, but you can get it approximate sparsity. Okay, and okay, so well, I have a little time left. So what I can do, probably I want to do this. I want to sketch you the proof of this, the idea of the proof only, okay? Just a very simple idea of the proof, okay? Not mentioning technicalities, okay? Technicalities will be only in one place, and I will just formulate what is needed, okay, in there. But there are some technicalities here, but the idea can be understood, okay? And then maybe I will show you, if you want, I will show you a modification of this theorem, in some sense a better version of this theorem that allows to choose epsilon independently on d that we don't know actually, right? We don't know which d to use, right? So it's kind of not nice that regularization parameter, is related in the condition to d in some sense, right? So I will show you how to phrase this differently, okay? So that it's a little different result, okay? That does not require this, okay? And then I will maybe have a little time left to talk about the sort part, the sort question, right? But if not, I think my talk at this workshop will be not the same, but on a similar topic. I maybe will be talking about different penalties and some other things, but there will be some time to talk about this later if I don't have time today. Okay, or you can always ask questions since I'm here anyway. Okay, so let me sketch the proof. Okay, let me sketch the proof. And what you have to look at, the minimization problems, okay? Because I will write certain rather simple necessary conditions of extremum in these problems, okay? And everything will be extracted from there, okay? Will be extracted from there. So here are the conditions. So let me start. I don't know. I probably will use this. support. Okay, so this is not completely erased. So here will be, necessary condition of extremum in this problem, the way I need it. So essentially, I'm just differentiating this. It's a smooth function of lambda, right? So I'm computing derivative in certain direction, right? And the direction will be from lambda epsilon. This is where the minimum is, to lambda hat epsilon. Okay, and then it's just an easy computation. You can check it for yourselves, that the answer will be this. This is what I'm getting when I differentiate the penalty, right? And I'm differentiating in the direction from lambda epsilon to lambda hat epsilon, right? To lambda hat epsilon. And then what is going to happen? It's going to happen that this will be greater or equal than 0. Okay, greater or equal than 0, because I am moving from one point in the simplex to another point in the simplex. Both are in the simplex, so I'm moving inside the simplex, right? In a way. Okay, I'm moving inside the simplex, and this is gradient, right, of my function. It's smooth. It's at the same time subgradient, right? And then you can just it's very elementary. Okay, you can see that since the function increases in this direction, we should have this thing greater or equal than 0, right, in this direction. Now, similarly, I will do just the same exercise for this problem, right? And for this problem, I will be computing the derivative at lambda hat epsilon, but I will be moving still from lambda epsilon to lambda hat epsilon, and then the derivative will be negative, right? It will change sign, because I am moving now to the point where there is minimum, okay? Where there is minimum. So I just will write this. So we just want to have the same thing here as here in order to subtract one from another, of course. Just to do algebra. So here I will have lambda j hat epsilon plus 1, lambda j epsilon minus lambda j epsilon, and this will be less or equal than 0. This will be less or equal than 0. So one should feel an irresistible impulse to subtract this line from this line, and also to replace here Pn by P, and to take the difference to another side. Okay, this is the whole idea here, okay? And this is what I'm doing. So I'm replacing Pn by P and subtracting from this line. So what I will get? I will get L prime f lambda hat epsilon minus L prime f lambda epsilon times f lambda hat epsilon minus f lambda epsilon plus epsilon, and then I have to subtract it here, right? And I will get lambda j hat epsilon divided by lambda j epsilon, the difference of two logarithms, and multiplied by lambda j hat epsilon minus lambda j epsilon, right? And if I had here Pn and P, I replace Pn by P actually here, right, in order to get this expression. If I had Pn not P, then I would have, it will be less or equal than 0. I'm subtracting from negative number, positive number, right? It will be less or equal than 0. Here, it's not going to be 0, it's going to be some error that I made when I replaced one thing by another, so I have to write this error. It will be, let me write it this way. It does not matter much. I take absolute value, and this is what we are getting on the right-hand side. Okay? This is what we have on the right-hand side. Okay, now we just have to understand what is what. So this thing here is just Kullback-Leibler symmetrized Kullback-Leibler distance between lambda hat epsilon and lambda epsilon. It's straightforward. Okay, just symmetrized Kullback-Leibler distance. This is where it comes from. Now, this thing here I would replace by a lower bound, right? Because I know that my loss function L is continuously differentiable and is convex, right, with respect to the second entry, right? And the derivative, the second derivative, is bounded away from zero, right? Is strictly positive, right? These were the assumptions I made, that the loss is of quadratic type. Right? So it means that L prime is a strictly increasing function and its derivative is bigger than zero and bounded away from zero. As a result, you know, this product, by the way, of course, is non-negative, right? Because this function is increasing, right? So when I multiply these two things, it's non-negative, but moreover, it will be bigger than the square of the L2 norm, right? Between f lambda hat epsilon and f lambda epsilon, right? So I can bound it from below just to make my life easier, okay? So I replace this by lower bound and writing constant. Constant depends only on the loss function, on the second derivative of the loss. I write constant times f lambda hat epsilon minus f lambda epsilon square, right? This is precisely more or less the thing that I want to control, right, in my inequality, right, that I want to control. And I'm already controlling it, right? I'm already controlling it. Constant times this distance, square of this distance, plus epsilon times Kullback-Leibler distance, right? I'm already controlling it, but I'm controlling it by something messy, right? And I have to figure out from this how to control it nicely, right? How to control it nicely. And what is helpful here? What we have here is the difference between empirical distribution and true distribution. So it's some kind of empirical process, right? Some kind of empirical process. And then just because of the law of large numbers, right? Pn is getting close to p when n is large. By the central limit theorem, should be something like 1 over square root of n, right? The order of this thing, right? Of course, it's all just means hand waving because these vectors here are high dimensional, right? They are in capital N dimensional space, and capital N can be bigger than this, right? But basically, what makes life good, kind of nicer here, okay, is that okay, because of the reason that this is the right-hand side is supposed to be small, right? This makes f lambda hat epsilon close to f lambda epsilon in L2 distance, right? And you see here I also have the difference between f lambda hat epsilon and f lambda epsilon. So it makes the right-hand side even smaller, right? Makes the right-hand side even smaller. In addition to this, it's easy to observe that Kullback-Leibler distance allows to control sparsity in some sense, right? Namely, one can write the following very, very simple bounds, right, that you can easily derive. That some, it's for any set J, you will have this. Okay, this is what we will have, and also another way around, of course. This is a very, very simple observation, and you know, it tells us that if Kullback-Leibler distance is small, and it is somehow, you know, we have some control here of the Kullback-Leibler distance in terms of something that is small, right? In terms of something that is small. Then this would make, provided that this vector is sparse, right? Is approximately sparse. This would make also this vector in some sense approximately sparse, right? And the fact that this vector is approximately sparse should make empirical process in the right-hand side even smaller. So it's small for several reasons. One reason is that usual effect of the central limit theorem, say, right? that makes the difference between Pn and P small. Another effect is that lambda hat epsilon is sparse vector, right? Has some sparsity in it, right? And this should make easier to control this right-hand side, right? And also these two functions are close in L2 sense, right? So the kind of which means essentially that the variance of the random variable that we have in this empirical process, right, is small. So if we have empirical process on a function with small variance, it becomes even smaller, right? It becomes even smaller. So these are basically what should be exploited here, right? What should be exploited. And the way to do it is to write to invent essentially certain bound. You can introduce this expression. So it will be supremum of Pn minus P. I will just copy more or less what we have in there, except that I'm replacing lambda hat epsilon, which is a random vector, by something non-random, and I'm taking supremum over such vectors, right? And then what I will do, I will take supremum over vectors from lambda, and I want sum over j not in j of lambda j to be smaller than, to be controlled by some number capital delta that is written here, right? And I want the distance between f lambda and f lambda epsilon to be controlled by this number delta small. By this number delta small. Okay, this is what I have, right? So with this, I can replace what is written here just by alpha n. The way I wrote it, it will be just this, right? This distance plays the role of delta small in my case, right? And whatever this thing is, this is my delta capital, right? My delta capital. So in a way, I am getting some inequality here, right? Inequality that controls this guy, right? The square of this distance in terms of something that depends also on the same distance, right? And I have here some measure of non-sparsity of lambda hat epsilon, right? Some measure of non-sparsity of lambda hat epsilon that is sitting here, right? And I have also something similar in the left-hand side because of these bounds, right, that control how non-sparse, say, lambda hat epsilon is in terms of Kullback-Leibler distance, right? In terms of Kullback-Leibler distance and in terms of the degree of sparsity of lambda epsilon, say, right? This is what I have, okay? This is a combination of several bounds that I have. And now in order to get something from here, I just have to construct an upper bound on this supremum that holds with high probability, right? Holds with high probability, and that would allow me to get an explicit inequality, right? So some inequality that I can solve then and get explicit bounds on delta small and delta capital, right? That's all that is needed. And it happens that with probability, and this is kind of the only technical part of it, with probability that I stated, with probability bigger than 1 minus capital N to the power minus A, this can be controlled by something like this. It will be constant C, and then delta small square root of D plus A log N over N small, and it will be maximum with delta capital square root of D plus A log N over N small, and maximum of this thing. Okay, this is an upper bound that you are getting, okay? And this is technical thing, right? To derive this upper bound, you have to use some machinery that is nowadays well known, but anyway, it has to be used. Lagrange concentration inequalities and various tricks like symmetrization inequalities, contraction inequalities. So it requires several pages of work, say, so to derive this bound, but it's anyway it's there, and then this gives you kind of expression that is good enough to solve the inequalities, right? Because the inequalities now are simple. You have something like C delta square here plus this thing you have to combine with this bound that allow to control sparsity, and then you're just solving these inequalities and getting the result, okay, that I claimed, okay. And okay, I don't know what to do next because I am almost out of time. If you should tell me, you can start asking questions, and depending if you want, and depending on this, I can either formulate you some other things that I have not said, or can leave it, for another occasion.
Does it make any sense to, instead of using the entropy penalty, using just a L2 penalty? Because then
No, L2 penalty is pretty bad penalty. The reason why L2 penalty is very bad is because of this for sparsity. I mean.
you'll get exact sparsity.
Sorry.
Won't you get exact sparsity because of the non-negative constraints on the lambda chains?
Well, but I don't think that the error term is going to be any good. Okay, if you use L2 penalty, you will end up with something like capital N divided by N. You are not going to get any control in terms of the sparsity of the solution. Okay, the reason is that roughly when you are adding L2 penalty, what very roughly. Okay, it's not a precise explanation, but. Okay, why we are not using L2 penalty in unconstrained problem, right? In unconstrained problem.
Oh, yeah.
Why we are not using?
Constraints here, yeah.
So no, okay, but why we are not using it in unconstrained problem, right? We are not using it because of the following reason. Okay, this is how I would explain this. Okay. Because when we add something like epsilon plus square of L2 norm, right? Plus square of L2 norm, when you are adding something like this, very roughly it means that you are trying to put your solution, right? To keep your solution in the L2 ball of radius 1 over square root of epsilon, right? So in L2 ball of finite radius. Right? Unfortunately, L2 balls, right, unlike L1 balls, for instance, right, L2 balls are huge in high-dimensional space, right? And if you start looking at expressions like this, and you inevitably will end up with some expressions like this, no matter which penalty you are using, right? If you start looking at expressions like this, and instead of having some control, right, some control in L1 norm, you are getting only some control in L2 norm, you are ending up with a huge size of this quantity, okay? It just will be of the order more or less capital N divided by small n. You cannot make it smaller than this, okay? You cannot get D over N by using L2 penalty, just because of the huge size of L2 ball. You have very, it's L2 ball is is always bigger than L1 ball, right? But in dimension 2 we don't see how much bigger it is. But in dimension 1000, L1 ball is nothing comparing with L2 ball. Okay. In this problem, of course, I have constraint, right? So I'm in the simplex. But it does not help me much, because I will have to take intersection of this simplex with some L2 ball, right? With some L2 ball, and it will be, I think, almost like not having intersection at all, like minimizing over the simplex as it is. And if you minimize over the simplex as it is, you will get error rate of the order, I think, square root of log capital N divided by small n. Okay, which is also not good because it does not take into account sparsity.
But Vlad, couldn't you also formulate it as saying, well, you're putting a penalty on L2 without being in the simplex, plus a penalty on L1 because you're requiring that the sum of the things be 1, and it's non-negative, so the sum of the absolute values be 1.
But I don't think...
And then that kind of penalty has been looked at. I think
This is elastic nets and things like this.
Exactly.
Elastic nets and things like this. But it's not the same, I think, in this problem when you are fixing the simplex, right? When you are fixing
Yeah.
the simplex, it's not the same type of thing.
You
Okay?
give yourself more freedom then.
Yeah, of course, when
You have two
of course when you are adding L1 penalty in combination with L2 penalty, right? I'm not saying that this is wrong, but you can add only L1 penalty and still achieve sparsity, right? So it's not because of this, okay? But you are not achieving sparsity just by, for instance, minimizing over L1 ball, right? Without doing penalization.
Can I just ask, also coming back to the thing you introduced actually, which was this anti-intuitive nature of the
Yeah.
of the penalty. Do you have any? I mean, yes, if one goes through the calculations as you did, but do you have any sort of more intuitive explanation of how this is happening?
Oh,
Of why that the penalty, which appears anti-intuitive, is actually doing what you want?
well, it did not look to me actually when I start looking at this counterintuitive, because before working on this, I did some other work that already is published, I think, this year in Analysis Institut Poincaré. And in this paper, I was looking at sparse recovery in the whole linear span, but with using not L1 penalty, but LP penalty, right? Not L2 also, but LP. With P, which was actually pretty close to 1. And by close, I mean this, of this order. Okay, 1 plus 1 divided by logarithm of capital N. This is actually, in some sense, the right size of P in this type of problems, because it already makes the problem strictly convex. Gives you some convexity modulus that is actually exploited in this argument, right? And I did the same argument in the case of LP penalty, right? Of LP penalty. And at the same time, okay, this penalty is strictly convex, but at the same time it's not that far from L1, in the sense that if you use this value of P, unlike the value P equal to 2, the LP ball is about the same size as L1 ball, up to a constant, okay? It will be, they're just of the same size, so you still have nice control of the things, okay? So with, if you are looking at LP penalty like this, that at the beginning just looked to me as a little relaxation of L1 penalties that makes things smooth and strictly convex and allows, to analyze the problem better, okay? But it already has the same difficulties, okay, that you intuitive difficulties, if you want, okay, as you have in the case of entropy, okay, because also when you can easily see that when you are using LP norm instead of L1 with P bigger than 1, there will be a tendency to redistribute the coefficients kind of uniformly, okay? Just think, in which case, this thing is going to be minimized, okay, when you are looking at this, okay? So when I came to the problem about entropy, okay, I already was pretty sure that this is about the same, okay? So I had no illusions about this thing. I knew that it's gonna work, okay, somehow, okay, I just did it, okay? Yes. So I did not have your questions, okay, about, I did not need to invent any intuitive explanation for this, okay, but I don't know, I don't feel that I know well at intuitive level why L1 penalization works, for instance, okay, with which all this started, okay. There are some people are trying to give some intuitive that, that this L1 simplex, is kind of, all these vertices, it's kind of many of them. When you start, you are hitting vertex, right? When you are, but it does not explain much to me. I for instance, okay, I need to see the proof actually in order to understand why it works. okay? In the case of L1 penalization, I don't think that intuitive explanations, even in this case, are very successful, okay? And if you are looking at something like entropy, of course, it's already not, you can't use convex geometry any longer, right? Because it's not kind of convex polyhedra you are dealing with, it's something, you know, curved in a way, okay? So it probably has less, there is less geometric intuition behind this, okay? But still there is some analysis that can be done.
I guess I was thinking about it, trying to think about it in terms of what happens if you start with epsilon large and start to shrink it. So in the case of the entropy penalty, maybe the counterintuitive piece comes about because if epsilon is large here, then your best solution in terms of the penalty is putting you right smack in the center of that convex hull, right? Whereas if you start out with more like an L0 or L1 type penalty, is putting you more like an L curl would put you at the extreme points of the hull.
That's true, but yeah, but even if you are using L1 penalty, you probably don't want to use very large regularization parameter, right? You are not going to solve the problem you want to solve.
There's a path, right, as epsilon increases to...
You know, I kind of tend to look at it as any type of regularization in statistics, okay? You need regularization for some reason, okay? And like in kernel density estimator, okay? You need regularization basically because it's hard to control random error when regularization parameter is 0. It's impossible probably to control it right, okay? That's why you need regularization, right? The same as in the case of kernel density estimation, you have to make your bandwidth positive, right? Your bandwidth parameter positive in order to be able to smooth things enough, in order to be able to control, to do probabilistic argument, to use some bounds, right? To see what is the accuracy in the law of large numbers, right? That is, to which it boils down, right? When you look at random error, right? In the case of kernel density estimator, and on the other hand, you don't want, of course, bandwidths to be too large, right? Because in this case, the bias or the approximation error would become large, right? And the same is here, right? If you use large epsilon, then you have to look at this last question that I have not talked about, right? In this case, of course, you're not going to get even close to the right solution just because the approximation error is going to be large.
On the simplex, the L1 penalty doesn't impose a penalty at all.
Sure. So yeah, of course, it's because it's L1 norm is already
But you
fixed.
still know that L1 is a proxy for L0 in the appropriate case. So if you
Yeah.
add in, as long as epsilon is finite, it's still the rest of you is pulling you.
Well, let's see what the following makes sense. I mean, there's the two parts of the objective function. There's
Yeah.
the quadratic part and
Yeah.
there's the entropy. And so suppose that you make a whole bunch of stuff 0, then and then the entropy redistributes equally for the
Yeah.
others. Well, on this side, you're getting a minus log times the number of points that you're on this side, on the other hand, you're getting something much worse because your quadratic penalty is really penalizing you. The quadratic part is really costing you much more.
Of course, you have to reach some
That's how
balance,
it's-
right?
it's-
Sure, you have to reach some balance. If there is as I said at the beginning, I think if there is a sparse vector that makes the empirical risk very, very good, very small, right? And this problem, of course, you cannot, the entropy cannot do much harm, right? It's going to put some coefficients in order to make them to stay away from 0, but in such a way that it would not spoil too much the first term, right? So in this case, precisely what is happening, we are getting, instead of getting strictly sparse solution, we are getting approximately sparse solution.
Yeah.
But still, the error is controlled the same way.
That interpretation is, I guess, something about expanding through the logarithm, this kind of region of admissible compressibility, right? I mean, it's like you're sort of using the log as sort of stretching out that region of getting close to 0 all the way out to getting close to minus infinity somehow. So it's this sublinear, I guess it's like the sublinear or the sub-additivity of the penalty that's interesting. Yeah.
Anyway, it's written, it works for whatever reason, so I've never tried it in practice, so I don't know whether it works in practice, but yeah.
Well, the nice thing about it also is it's such a nice, it's not just strictly convex, it's, you know, it's smooth.
Well, you know, I kind of another thing that I did in this paper. It's of course very natural to look at a convex hull instead of looking at the whole linear span if you are estimating density, because in density estimation problem you would have probably rather naturally you can come up with a dictionary of densities, right? And then a large dictionary of densities, and then you are looking at the mixture of those densities, and you are trying to find, you know, kind of mixture here, and you can use this entropy penalization in this case. It's more natural probably than in prediction problems, but there are some prediction problems where you also can care about, I don't know, preserving shape or something like this, and then you want to look at convex combination instead of the whole linear span.
That's come up.
Yeah.
In some talks, as I recall.
Yeah, sure.
So do you think that there's some people who have proposed penalizations based on entropy, sort of assuming it will spread out things, and actually
Oh no,
what they're getting is,
there are many people that use this type of penalization,
Yeah,
but they I don't think they have ever observed that it's a way to enforce to kind of implement sparse recovery.
well, what I'm
Many people in machine learning who are
Which
using.
sign, though, do they use? Do they use the minus or do they use the plus?
Sorry? No. There are papers where they did more or less this penalization. You know.
So
maximum
what-
entropy.
That's
the
right.
maximum entropy conferences that
Yeah.
That's right.
edge
Max
chains
entropy.
as well.
But I guess here you're starting out with the assumption that there exists a compressible solution, like
Mhm.
a nearly sparse solution.
Yeah.
I don't think in the ordinary context of maximum entropy, that's not usually somehow a starting assumption.
Well, they're trying to smooth rather than.
You know,
It will
it's
be true in these applications you
it's-
see with wavelets and things.
it's not precisely, you know, kind of what is usually called maximization of the entropy, because here I'm maximizing only the entropy of these mixing coefficients, right? So it's you know, I'm not looking at the entropy for my kind of intrinsic
Here, the
entropy for
max-
my
the max
problem,
is actually
right?
the
So
objective
yeah.
function.
Yeah.
The entropy is really objective function when you're
Yeah.
maximizing the entropy rather than penalty.
Yeah, so it has a little bit different flavor, but anyway.
Well, they do use it in this kind of penalized maximum likelihood, putting a entropy penalty
Yeah.
on the likelihood, log likelihood.
so
Smooth. Instead of bridge regression, they shove in a.
Instead of L2, exactly.
Yeah.
This is
So
You,
my
what again you said, Mike? Oh,
It's true.
what
Well, for a long time there's been annual conferences about Bayesian methods and
max
and
ent
entropy.
or something.
Max
Bayes
ent, yeah.
ent or something.
Uh-huh.
Yeah.
I had a big argument with them in
Oh, no.
because they said this is the only bona fide regularization and
The one true
function
way.
you should
All right.
One true path.
Well, actually, wasn't
Way to differ.
this paper by I guess Ian and David Donahoe and
Yeah.
Stern and Office, the black object, wasn't that exactly showing that in fact there are other things you could do rather than that max entropy could work okay, but other things work equally well.
Hmm. You mean that RSS?
That RSS discussion paper.
I mean, it does go to your earlier question. Like, it is true in those contexts, people would have used L2 before. I mean, they would have done the standard ridge thing, and then they came along and sort of thought of. So there's a context where they would have done penalized likelihood within L2 with a ridge regression term, but they, as you pointed out, they came along and said, oh, well, we can smooth according to this wonderful principle called.
I thought that the only positive thing about the maximum entropy penalty is that you do not get anything that's negative. You cannot come up with a negative have you? Because of the law.
Yeah, so if you had a positive, you
It's
can
ridge regression. If you're trying to smooth an image, then you know that image intensities are not negative. If you're in danger of getting sparsity, you're using a quadratic penalty. Then by using the entropy, you don't get sparsity, therefore you don't get a negative image coming up.
So Vlad, getting back to your actual intuition here, I guess what I'm getting out of this is if I wanted to use a penalty like lambda to the 1 plus epsilon,
Yes.
I might as well just use lambda log lambda and
Yeah, well,
And-
it's
and then not have to worry
these
about it.
things are very similar
Yeah.
actually in many respects. You
Yeah.
know, if you
Yeah.
just use LP with P a little bit bigger than 1, analytically it's something very close to entropy.
Yes, because you can write it as lambda
Yeah,
e to the epsilon log.
yeah, exactly, yeah.
Didn't Mickey Ela produce some paper about what happens if you enforce positivity and sparsity, and it didn't matter so much how you penalize?
Again, what was the question?
Mickey Ela, they were testing. I remember going to some talk where he talked about enforcing both positivity and sparsity. It made less difference what penalty you use.
Remember now.
Can you read it? Just
Remember.
ELAB.
The only other concrete thing I could think of to get back to this question about whether it's counterintuitive or not is if you have, if I have two candidate lambdas and they both give me equal likelihood, and lambda 1 is obtained by averaging lambda 2, then lambda 1 will win there. I don't really know. I guess I mean, that's what entropy gives you. So somehow, I guess that's just telling you, like, that effect is somehow not strong relative to small changes in the somehow small changes in the likelihood are just inducing even smaller changes in the entropy or something.
Probably, yeah. Probably this is correct, yeah. But you know, the fact that something is counterintuitive matters only before you know the answer, right? When you already know the answer, it does not
so it
matter
only
that much.
happens once.
Yeah.
And then suddenly everything else.
Even the referee, you know, the referees could be very nasty sometimes. You know, he was very nice and just asked me to add some you know hints about this, you know,
Yeah.
so it was
Yeah.
not that,
Yeah.
you know.
If he was nasty, you could say this is clearly wrong.
Yeah, because my intuition tells me this should be wrong, and that's it. Yeah, there should be some mistake in the proof. It's your business to find it. Okay, I think I can remove this for sure.